Okay, so 233, this question. We had to find the third cosmic velocity. I didn't know what that is. They actually told us. So the minimum velocity that is to be imparted to a body relative to the Earth's surface to drive it out of the solar system. So the thing is, we are talking about the solar system over here, not the galaxy or anything. Right. So here's what's happening. You got the sun over here. You got Earth. Earth is moving with some velocity, so some speed. We'll just call it as v Earth, right? With respect to Earth, you impart some velocity to a body, right? Uh, of course, we would like our final final velocity in the reference frame of the sun to be the maximum. And so to do that, we actually have to impart it in this direction. So this is how the body's velocity with respect to Earth should be. So we'll just call it as v3, all right? So that's what they are calling, and that's fine. Right, so the combined velocity, so for this particle, the velocity in the reference frame of sun, that thing is just the v Earth plus v3, right? And now it's just yeah, the classic escape problem. So what we want is that this should escape, right? This particle should escape to infinity. Uh, yeah, taking this as the origin. And then we know how it's going to be. It's going to be some kind of parabola, like it goes like, you get the thing, right? So we want the minimum velocity so that that happens. It could be a parabola. If it's the minimum, if it's more than that, it's a hyperbola, whatever. Let's just figure out what that's going to be. So let's call the mass of sun as ms. What did they give us? Rotation of Earth about its own axis is to be neglected. Okay, whatever. They didn't give us what the mass of sun is, or whatever. So mass of sun, g times that upon yeah, okay, so 2 of that upon the radius. So the radius of what do we call it? What is this distance going to be? I have no idea. Um, yeah, so it seems it actually depends on where the Earth is, right? Yeah, it's kind of a weird thing. Hmm. Fine, whatever. We just assume it's circular orbits. Then it's just the distance between Sun and Earth. The distance, not the distance at a point. Okay, so you just got this thing. I don't know what to call this R. I'm just gonna call it R. Right, square root of that thing. That's the escape velocity. In this case, is just velocity of Earth. Why does it look like escape velocity over here? I mean, yeah, that's weird. Just call it U Earth. I don't know. Just leave it like that for now. As long as you know the context, it's not that hard to figure out what this thing is, right? Okay, so there we go. V3 is just equal to square root of 2gms upon r minus v Earth, right? Exactly. Yeah, that would be the thing, but here's a big problem. So we want this particle to escape the solar system. Sure, we want it to escape the gravitational field of sun. No big deal. But the thing is, there's also this Earth that is very close to this particle. So you also have to take that into consideration. So not only do you have to have enough energy to escape um, from the field of sun, but also the field of Earth combined, right? So the potential at this point is not, it's not GMS upon R. It's not that. Instead, it is this thing. It is G mass of sun upon, and let's call this thing as R, and we'll call the radius of Earth be RE. So G mass of sun upon R. It's negative and everything, I know that, but whatever. And then plus G mass of Earth, all right, upon the radius of Earth. This is the potential at that point. Okay, negative of that. And yeah, so just do the energy stuff, and you will get the thing that 2 times of that, the square root of that thing. This is the value for VE plus V3 actually. And now you can actually do the thing. Cool. Also, we actually know what V is, sorry, what VE is, since we know that Earth is just orbiting around the sun. So VE is just equal to square root of GM sun upon R sun, right? and then you can just use this thing to get V3. Cool. Uh, yeah, let's do the thing. So you got, okay, let's simplify this. Um, wow, this is getting complicated, isn't it? Okay, think about it. V3 is just equal to square root of 2g, and then you got mass of sun upon radius. Okay, we should not say radius of sun, it's the radius, so this r value. Okay, plus mass of earth upon radius of earth, right? Starting to think maybe you can approximate it somehow using binomial theorem, but whatever. And minus the velocity of earth, which is just square root of this thing. So yeah, g mass of sun upon the r value. So where is that g? There should be a g over here, not a 2. So g mass of sun upon r. Cool. And I think somewhere it was written in a different form. So they only used VE. They never actually used this stuff, right? So let's try it in that way. So it's going to be square root of, you got this 2gm earth upon r earth, right? But then this whole thing we can write that as just 2 the earth square, and then that thing minus this. So does that make sense? I don't know. I think it should. It's got this thing, so it's the earth. I think there was a different formula for this as well. Yeah, right. There was probably a different formula for this thing. I don't remember that. But anyway, that's my take. This is the way it should be, I think. So if we want to escape the solar system, I think that's what's supposed to happen. That, yeah, sure. What would go wrong? Well, maybe you could like approximate this a bit. So yeah, we could actually approximate this. Why not? Let's do the thing. Let's try to approximate. So yeah, we know that velocity for Earth is actually very big. Um, yes. So this is what the velocity of Earth is, and then you got this other thing. So this is the escape velocity from Earth, which I think is not that big. It's 11.2 kilometer per second. And what's the velocity of Earth? Okay, I don't have any idea for. So maybe it's not good to do approximations right now. Right, I'll just leave it like that and not go any further. Wow, but I really think there was some other approximation that we could do. It's just that I don't remember what that was. But anyway, this is the thing. So this is our V3 value. I think this is the better thing to do. And yeah, instead of all that V escape and stuff. Yeah, so velocity of Earth. So V is not V escape. It is velocity of Earth. Okay. 233 done. So to the next section. Okay, dynamics of a solid body. Equation of dynamics of a solid body rotating about a stationary axis. I know these things, all right? Don't tell me this. What's this thing? Work done by external forces during the rotation of solid body about a stationary axis A equal to. Okay, they won't actually explain whatever this symbol means, right? Because they already told you that you should already know what this symbol. Okay, I don't know. I don't know what these symbols mean. But yeah, I'll find it out by myself. I don't need your help. Okay, let's go. 234. What's the thing? A thin uniform rod AB of mass something. Mass is what, 1. Moves translationally with acceleration. So you got a rod. Okay, it moves with acceleration. What? So W is equal to 2. So it moves with that acceleration. Okay. Due to two anti-parallel forces F1 and F2, 1.52. Where is the figure? Oh, so like this thing. What happened? Why is this on work with me? Okay, so the acceleration is W. Right. What else is given? The distance between the points at which these forces have to be applied is equal to A. So A is 0 0.2 meters. Right. Besides, it is known that F2, we just gave the value of F2. F2 is 5. Find the length of the rod. So what is the length? Okay, cool. It's gonna be easy. So, right, F2 minus F. So you know what F2 is, right? And where is W? Well, F2 is given as a bigger value, so we'll assume it's going to the right. Right. So F2 was 5. 5 minus F1 is equal to M times A, which is, sorry, M times W. In this case, A is a different thing. It's just confusing, isn't it? So F1 is equal to 3, right? So you got 5 in this direction and 3 in that direction. Cool. And about the center of mass, yeah, just got that thing. Cool. No big deal, right? Okay. Yeah, so all these points are moving translationally. I want to take the center of mass, but well, whatever. We just do the thing. So, right, F2, which is 5, 5 times this value. So, what is this value exactly? It's just L upon 2 minus A, right? Okay, that is equal to F1, which is 3 times L upon 2. Yeah, that should do the thing. So, right, 2 times of L upon 2, it's equal to 5 times of A, I think. So L is equal to 5A, and A was just 0.2, so it's going to be 1 meter. There we go, 1 meter. Next, 235. 235 is a force F is equal to A plus AI plus PJ is applied to a point whose radius vector is okay related to the origin of coordinates. O is equal to this thing. All right. Find the moment N and the arm L of the force relative to the point O. Arm L. Oh, okay, that component of R vector that is perpendicular to F, right? First, we just figure out what arm length is, right? So what is L? Uh, F is given. What else was given? K is equal to R is equal to A plus BJ. What I'm thinking is instead of doing all that, instead of actually figuring out L first, we can just figure out the torque, right? And okay, they're calling the torque as N. This is a very bad, uh, really, N of all things. Why that? Well, whatever. I'm just gonna call it torque. So tau. Yeah, just R vector cross F vector about the O point, right? Yeah. So R is and it's a point mass. Yeah, point mass. So this thing A comma B cross. What's the F vector? It's just capital A comma capital B. That just equal to B A minus minus B A, right? And that is actually equal to the magnitude of force, which is square root of A squared plus B squared. That times the length. So the length is, we don't know what that thing is. So it's the arm, right? L is just equal to this thing, BA minus BA upon square root of A squared plus B squared. That's all you need. And yeah, we are going to call this N. I don't like it in that way, but whatever. And it's in the K hat direction. So yeah, let's make it like that. N hat is equal to this stuff in the K hat direction. Okay. Why do they use these weird notations? Everyone uses tau. They are using n. Okay, 236. A force F is okay. AJ is applied. No, F1 is equal to AJ. Hey, so a figure is given us. Is the figure given to us? No, right? Okay, F1 is equal to AJ is applied to a point. Let's just write that down. F1 is equal to 0 comma A. Okay, whose radius vector R1 is AI, so it's A comma 0. um, okay, these are of course vectors, and a force 2 is equal to B comma 0 is applied to a point whose radius vector is R2. Seriously, I mean, are you really going to make us calculate this thing? Both radius vectors are determined relative to the origin of, okay, come on, see, right? What do you want? Find the arm L of the resultant force related to point O. Okay, no big deal. Ah, this is so not good. Fine, just figure out the torque. So our torque is m in the k hat direction. Of course, we're just gonna, you know, think of it as a scalar because it's in the same direction. We know that it's just k hat all of the time, right? For a planar motion. Okay, so r1 cross f. Do I even have to do this thing? ai hat and then aj hat is just aa, and then this is in the opposite direction. So j hat cross I hat is just minus bp, right? The resultant force is just p comma a, right? So this is equal to L times square root of, why is that happening? Okay, square root of p square plus a square. There we go. We got the arm length. Same thing as the last time, isn't it? No, okay, last time you got this. It's opposite of that. Fine. Yeah, this should work out. So there we go. What do you want to find once again? Arm L. That's all you want to find, right? Okay. Well, if you think about it, these should be in mod values because who knows, the torque might actually be along the negative k hat direction, and then yeah, yeah, right. So yeah, that would be weird, isn't it? L is always going in that direction then. So what does that mean if L is negative, right? So in our idealized condition here, L is actually going like this, and that's your net force, right? Okay. So it's in the k hat direction. What if it's not? What if it's not in the k hat direction? Then your actually force is in this direction. And yeah, okay. You should take the magnitude in that case all the time actually. Right, so it's still the same thing. Yeah, this much. Isn't it the same as the last question? It is. The next question. 237. 237 is, okay, the forces are applied to square plate. Okay, figure 1.53. Find the modulus direction and point of application of the resultant force if the point is taken on the side BC. But oh, so on this, right, there's a point where if you apply the net force, you will get that same torque, right? What is the net force actually? It's just F in that direction, F in that direction. Okay, that cancels. So just 2F in this direction. So net force, F net, is just 2F in the I hat direction. Okay, what's the total torque? And what is our origin, by the way? Well, okay, they didn't give us anything. Uh, huh, that's weird. We'll just do it about the center of mass, of course. So about the center of mass, just figure out torque and everything. Yeah. So you got F in that direction, F in that direction. Yeah, basically this is the thing. So okay, that is going to be not important. Just got F in that direction, and then this is F in that. Hey, don't these two torques cancel each other out? Of course they do. Then just this thing. So you got this, which we just call it R for now. It's F times R, right? It's our torque, and that's equal to, okay, maybe we should not call it like that. We'll just call it, okay, this is actually just A upon square root. If the side length is A, and is anything given to us about its dimensions? No, nothing is given. Why? You want the point of application, you should at least give us coordinates or something. How am I supposed to tell you then? Okay, I'm just gonna tell you if it's a special point or something, like the midpoint of BC or something like that, or trisection points, or who knows. So FA upon square root 2. Okay, that's the thing. Now, yeah, you got F in that direction. You just, the R vector, you just need to take the arm length first of all. So that, yeah, like the basically Y coordinate, right? So the Y coordinate of whatever that point is, times 2F. Sure, sure, that should be the thing. So Y is equal to A upon 2 square root 2. And no, it's not even. Ah, why? Okay, y equal to a upon 2 square root 2. How does that even make sense? This thing is, that is a upon square root 2, right? Yeah, this thing is a upon square root 2, this thing is a upon square root 2. And then you got a upon 2. Oh, it is actually this point, right? This is the y coordinate you're looking for. So it is in fact the midpoint of BC somehow. Wow, that was nice. So you can actually tell without the coordinates. So midpoint of BC. And also what else do they want? Resultant force, the modulus direction. Yeah, I mean, we already know that thing. So F net is just this thing. And you got the point. Cool. Next, 238. Just wait a second. Why did I always forget about that one? I don't know. Find the moment of inertia of a thin uniform rod related to the axis which is perpendicular to the rod and passes through its end. So axis, rod, what moment of inertia if the mass of the rod is m? Seriously, I mean, I know that already. It's just ml squared upon 3. Do you really want to integrate and get it out? No, I won't do that. You can do it yourself if you want. I won't. Okay. Of a thin uniform rectangular plate related to the axis passing perpendicular plane of plate to one of its vertices if the sides of the plates are equal to the whatever. So this is perpendicular axis theorem, right? Yeah, and you just got like ml squared, so ma squared upon 3 for this axis, right? So you got this as the plate. You got these two axes, right? About this axis, you might have this thing. This is A, this is B. Ma squared upon 3. And then you got mb squared upon 3, right? Sure. About this axis. There we go. So then just add them up to get the inertia about this axis, which is actually perpendicular plane. Cool. So just m times a squared plus b squared, all of that upon 3. Cool. Next question. 239. 239 is calculate the moment of inertia. Okay, these are like simpler questions than what I thought. So for copper, uniform disk related to symmetry axis perpendicular to the plane of disk that's mr squared upon 2. If the thickness is equal to this, what do you mean by the thickness? And its radius is, oh no, I need to know the density of copper for this thing. But I don't. So then how am I going to do this thing? So yeah, it's like mr squared upon 2, of course. But for m, you would need this thing. So you got pi r squared times the thickness, that's the volume, that times the density of copper, that times r squared, so like m r4 actually. Sorry, pi, whatever, that thing upon 2. This is a formula, but then you need the density to do this thing. And I don't know that. So I'm just gonna leave it like this. Yeah. And its radius is r, its thickness is b. Okay, so this should be nice. Yeah, next question. Why do they think I would know the density of copper? Okay, they have given us an index, so you can check it up and put it into this thing, get the value. But I can't do that when I'm solving the question. Okay. B. Of a uniform solid cone related to a symmetry axis if the mass of cone is equal to m and the radius of its base is equal to r. So inertia of a solid uniform cone. Why does it look like? Oh, that's weird. Okay, so yeah, no big deal. Uh, Wait, if it's a hollow cone, I can actually do it very easily. But for solid cone, it's kind of more complicated. Uh, yeah. Okay, you have to figure it out by integration this time. Let's do it. So you got this solid cone. This is our x coordinate. We just call this x coordinate. You got some angle. Let's just call it alpha. I don't know. This right. We'll call it r, small r. Right. This big thing is capital R. This whole thing we'll call it height h. Okay. The mass of this cylinder, right? We will figure that out. No big deal. So the mass of the cylinder is just the volume of the cylinder, which is 1/3 pi r square h times the density. Okay, I should use this thing. Capital R squared, capital H as the density. So you can figure out the mass later on. First, we'll just deal with density. Okay. So what's our di value? So for this frustum of a cone. I don't know, whatever you want to call it. It's just kind of like a disk. So it is mr squared upon 2. What is m for this thing? What's the volume? It is pi r squared. Yeah, okay, that times dx, that times rho. This is our mass. Okay, and you got r squared times this thing. So yeah, it's gonna be r power 4. And all of that upon 2. Cool. Looks very similar to this thing. Yeah, it is, of course, because it's a disk. Isn't that obvious? Okay, and then we just want to integrate this thing. So what we could do is just say x is equal to r upon, well, you know what? Yeah, we don't need this alpha anymore. I'm just going to use ratios. So x, for now, don't do that. Yeah, x upon r is just equal to h upon capital R. So x is just equal to this thing. So dx is this, h upon capital R, and then you got dr. Cool. So that's our di value. Is that correct? It must be. What could go wrong? Yeah, it must be. Must be. And now I just want to integrate this thing. So got rho pi h upon 2r, r power 4 dr, so it's like r power 5 upon 5. And it goes from 0 to capital R. So you got capital R power 5 upon 5. 5. Okay. Which will be rho pi h r power 4 upon 10. And yeah, our mass was this is our inertia, and our mass was this thing. So just do I upon m for now. So I upon m, that will be this upon that. Well, look, pi. Oh, you got r squared. Why is there no r squared over here? Oh, because it's gonna be there. Okay, fine. So pi r squared h and rho, all that cancels except you just got r squared. And then you got upon 10, but then 1 upon 3, so 3, right? So inertia is just 3 upon 10 m squared. Nice. You got a new formula. So, wow. Right. 3 upon 10 mr squared. Nice. So for a cone, inertia is this thing. Awesome. Next question. 240. It's like for a cone. I'm just gonna write it down because later on I'm going to copy this. And I should like make a list of all kinds of different inertia, right? Yeah, I should, because that will be very helpful for revision. Anyway, 240. Right, radius is given. Yeah, okay. 240. Demonstrate that in case of a thin plate of arbitrary shape, there is the following relationship between the moment of inertia. Okay, subindices denote mutual perpendicular axis passing through one point with axis 1 and 2 lying the plane. Oh, just a perpendicular axis theorem. Seriously, this is just a piece of cake. So you got this as your axis, you got this weird shape, it's planar, right? This is our I3 axis. So for a small element of dm mass, what is the inertia contributed by this thing? So got dm. Or let's say, think of it as discrete masses. I know it's not correct to do that, but whatever. Because it's a continuous body, well, whatever, doesn't matter. So you got mi. Sorry. This is our x coordinate. This is our x coordinate. This thing is y coordinate for this guy. So mi times x square, that's the inertia contribution to this thing, right? So summation of that, it's called xi actually, right? This is what, I1 or 2, I don't care about that. Whichever one it is, 1 or 2, we don't care. I2 is similar, just summation of mi yi squared. So this thing is just the inertia about this axis, I1, and I2 you got about this axis. This is 1, this is 2, this thing is the third one. I3 is on the other hand equal to summation of mi ri squared. Ri squared is just xi squared plus yi squared, and this is like trivial. It's trivial. The perpendicular axis theorem is really trivial. You can just get it in your head. So of course I3 is equal to I2 plus I1. What's the big deal? Next question. Do they really have to prove this thing? No. Okay. Right. Next. And what, using this relationship, find the moment of inertia of a thin uniform round disk of radius r. And mass m related to the axis coinciding with one of its time. Oh, come on, seriously. So done. And other one is just mr squared upon 4 because about I3 it's mr squared upon 2 and then symmetry. So I1, I2 are same mr squared upon 4. Right, 241. A uniform disk of radius r has a round cut as shown in the figure 1.54. Okay, the mass of the remaining shaded portion of the disk equals this thing. Okay, whatever. Find the moment of inertia of such a disk related to the axis passing through its center of inertia. Wait, what? And perpendicular to the plane of the disk. So, oh, this is bad. Center of inertia and perpendicular. But now the disk is not like, what? This is bad. Uh, yeah, you will have to figure out the center of mass in that case. Oh, I don't want to do this thing. So whatever. So this complete guy just has the center of mass at this point. You got a negative mass attached. You can think of it like that. A void is just a negative mass basically attached to this. Yeah, and it's got mass. Well, its radius is half of that. Like it's got m upon 4. Okay. Yeah, this is m. So right, we'll do that later on. We just say this big disk had mass m, and its um, center of mass is x coordinate versus 0. Then this disk has mass. So the negative disk that we have is just having mass negative m upon 4 because half the radius on 4. What am I writing? And its center of mass is at negative r upon 2. All right, and all of that upon the total mass, which is just m minus 3m upon 4. Isn't that right? Oh, sorry, not m minus m upon 4. That's the total mass. Yeah, so this thing plus that, whatever. So you just got how much? This m cancels r upon 8 upon 3/4, which is r upon 6. Yeah, so it's r upon 6 on the x-axis, which is at this point, right? So you got that thing now. Okay, so OC is just r upon 6. Okay, cool. We can figure out the inertia about point O, right? That's much easier, I think. And that's going to be mr squared upon 2. That's the initial inertia. Now minus the inertia of the thing that you deleted, right? And it's about this. Why is that about this point? Okay, whatever. So you got this. What was the mass once again? M upon 4, right? Then you got the radius is just r upon 2 squared upon 2, all right? Yeah, but parallel axis theorem, it's actually about this thing. So m upon 4, and then you got r upon 2 squared, cool. Which is, so you got 1 plus 1 upon, like 3 upon 2 of this. So mr squared upon, that's 4 and 4, 16, right? So 3 mr squared upon 32. It's going to be just this thing. So 3 mr squared upon 32. Perfect. And also, by the way, what is the small m magnitudes of capital M? So small m is just 3/4 of capital M because 1/4 of m is gone, right? So you can use that to get m in terms of small m. Just put that in there. Hopefully we get something nice. So 60 minus 3, which is 13 upon 32 mr squared, which is basically 4 upon 3 small m r squared. Okay, capital R squared still. Right. It is, why is it taking so long? Okay, it's got 8 times 3 is 24. So this is the thing. Right, that's our inertia about O. Let's just figure out the inertia about C in this case. Yeah, so for C, just gotta do this thing. So using parallel axis theorem, just got this minus the mass times the radius, okay, the distance actually, r upon 6 squared, right? Yeah. So it's like mr squared, and then you got 12 upon, sorry, 13 upon 24. I have no idea why this is taking so long, and most likely it's going to be incorrect because after doing a lot of calculations, you get incorrect results. Yeah, that's That's scary actually. Uh, am I sure it's correct? It must be. But yeah, you got, that's just 1 upon 2, so you got 3 upon 2, 3 upon 2 m r square, 3 upon 2, m upon 4 r upon 2 square is supposed to be this thing for 16, and then you got, sure, so that's right. Till this, it's just correct. Then you got 16 minus is 13, but yeah, this is also right. 24, why did I get 24? This was not supposed to be 24, it's supposed to be, oh, okay, because I converted to small m. Right, it was 13 upon 32 capital M r squared, but then capital M is just 4/3 of small m. Uh, yeah, so right, it is correct actually, no big deal. So 13 upon 24 minus 1 upon 36, sure. So small m r squared, take 8 out, no, 4, well no, 12, take it out. 13 upon 2 minus 1 upon 3, I think, right? This is going to be what? 39 minus 2 is just 37 upon 6. So mr squared upon 12 times this thing. So actually it's going to be like, okay, 37 upon 72 mr squared. Why? Okay, whatever. That is the thing. That's IC. It should, you know what? Let's keep IO over there as well. So IO was just this thing. So IO is this, and IC is this. It's 13 upon 72 mr squared, hopefully. Next question, 242. Come on, 242. Let's do it. So using the formula for moment of inertia of a uniform sphere, okay, find the moment of inertia of a thin spherical layer of mass m and radius r related to the axis passing. Okay, okay, this is actually a nice thing. Yeah, so I did think about this, but I never really thought about actually formalizing this. But yeah, now I can do it. So we know um, that for like a uniform sphere, the inertia is given by this thing, 2/5 mr squared about the what do we call it? About the diameter, right? So yeah, sure. Now if you, okay, this is maybe not the best way to do this thing. Uh, okay, there is a better way. I just don't want to say that. Yeah, but what other choice do I even have? So there is the better formula of 2/5 m r2 squared minus, sorry, r to power 5 actually. Uh, yeah, r to power 5 minus r1 power 5 upon r2 cube minus r1 cube, which you can use directly to get the thing, but I don't want to do that. All right, we can use this and just, this is like delta r power 5 and this is delta r power 3. So differentials just become, 5 r power 4 dr, and this is going to become 3 r power 2 dr, and then dr's cancel. You get the thing. You just get 2/3 of mr squared in that case, right? So this is when the mass of the body is constant. You can just use this formula for variable r to r. I know you won't get a physical process with that, but yeah, that's you can use. Sure, but I don't want to do that. Instead, I really just want to rely on this thing. Uh, yeah, first thing we'll do is actually convert this using, you know, densities and stuff. So the mass is just 4/3 pi r cubed times the density. So there we go. This is the thing. So our inertia is just this. It is 8 upon 15 pi rho r power 5. All right. So our ti value, as your r increases a bit, that's going to be just the inertia of the shell, right? Which is a differential quantity, of course, but trust me, I can make use of that. So it's going to be 8/3 pi rho r power 4 dr. Now, think about it. 4 pi r square times dr, isn't that just the volume of that? Yeah, isn't that just the volume of that spherical shell that you're adding? So it's just actually equal to So and density times that is just a mass, right? So it's a 2/3 of dm times r squared. Isn't that right? So di upon dm, right? That is going to be this thing. So for that little spherical shell, you get this thing, right? Now just generalize this thing because the geometry is the same. Okay, you get the thing, right? So inertia upon the mass of the spherical shell is, sorry, the, what is this once again? Uh, yeah, okay, a thin spherical shell, right? A thin spherical shell. Okay, I upon m is just equal to 2/3 r squared all of the time. Not just for the differentials, but all of the time, right? I know it's kind of a cheat to do this thing, but does that really matter as long as you're getting the same result? So I is just equal to 2 upon 3 r squared times m, exactly what we would want, right? So yeah, I just showed you two ways of doing this, but only one of them actually uses the original formula. Other one is not the original formula, it's modified, whatever. So yeah, I mean, other one is actually better if you want to go through the limit actually. This one is better if you think about differentials all the time, right? So 242 done. 243, a light thread body of mass m tied to its end is found on, okay, figure 1.55, this thing, fine, is wound on a uniform solid center of mass m in this r at moment equal to 0. System is set in motion assuming the friction in the axle of the cylinder uh, to be negligible. Oh, okay. Find the time dependence. Wait, what? Friction in the axle of the cylinder. Fine, fine, fine. Uniform solid cylinder of mass m is r, and it is wound to it, so it doesn't slip, I think. Find the time dependence of kinetic energy of the whole system and the angular velocity of the cylinder. Fine, no big deal. You do the thing. Just want a time dependence, right? So it's 1.55 for this case. Cool. So you got some tension, whatever. You got tension pulling down like this thing. You got tension of, yeah, you got small m. I mean, I could just use energy conservation. Why not use that, huh? Sure. If this goes down by x, right, and it acquires velocity of v, and then you can just do, yeah, you can just do energy conservation, and that's actually going to work because this guy has zero friction on it, and there is literally no force that can do work on this thing, and then there's only gravity doing the work on this guy, right? Yeah, but no, let's use kinematics instead. So right, what do you have? uh you got g in the dash, what, fine, whatever, it's like g minus t upon m, that's this guy's acceleration. This is equal to the acceleration of this guy, which is t times r upon the inertia. It's just a disk, I think. Is it a disk or it's a ring? What geometry? uh Wait, where did it go? Right, this thing. Solid cylinder, right? Then it's kind of a disk. Okay. The z-axis doesn't matter. Okay. So you got mr squared upon 2 as the inertia. But then this is just for alpha. You want this times r to get alpha r. That is the acceleration of this point. There we go. This is the thing. 2t upon m. Yeah, that's pretty much the stuff. So you can figure out t through this. Oh, it's small m, by the way. Looks like capital M, it's small m. T times 2 upon capital M plus 1 upon small m is just equal to g. There you go, you got the tension. Okay, this is not that. Ah, hmm. We involve a lot of. Okay, we could do this thing. We can just say that capital M is equal to eta times small m, right? Yeah, and then it's gonna become better. So t upon small m, and then you got 2 upon eta, all that stuff, right? Okay, so 2 upon eta plus 1 is equal to g. So you got t upon small m is 2 plus eta upon eta. Yeah, whatever. T upon m is just equal to eta upon 2 plus eta times g. Just put that in this thing and get the acceleration of the small m guy. So g minus this guy, which is 2 upon 2 plus eta times g. That's what the acceleration is. Now, what do you want? You want the angular velocity of the cylinder as a function of time. So Hey, its acceleration is actually constant, isn't it? So like a times t, you will get the thing. A times t is that velocity. So and that thing upon r value, you're gonna get it. Yeah. So 2 upon 2 plus eta g upon r times t. There we go. You got the velocity, angular velocity. Sorry, the kinetic energy of the whole system. Okay. Think about it. I don't want to do the kinetic energy and stuff. It would have been better if I just did that. Okay, whatever. Right, the energy of the whole system. You can just do the force on the net system. Okay, okay, like what is the thing? The power of the net system. That's just the velocity of this guy, right? And then you got the force of gravity pushing it, pulling it down. And anything else? No, there's no other way of putting in work. So there we go. That should be the thing. So it's just mv uh, times, yes, it should mg times v. Okay, mgb dt integration from 0 to t. Yeah, that's our work done on the system, which is our kinetic energy as well, actually. So it's a work done by gravity, right? The net work done, whatever. Okay, what's v? V was just 2 upon 2 plus eta times gt. So mg times 2 upon 2 plus eta, and then you got g, and once again a g. So okay, that g's out anyway. And addition of this thing from 0 to t, and it's got t dt, I think, because yeah, sure, this should be correct, I think. Is it correct? You got a g square somehow. Why did that happen? I don't know, but that did happen. Okay, whatever. So it's got 2 upon 2 plus eta times mg square, and then this integration just t squared upon 2, whatever. So this is just 1, and then you got t squared from 0 to t. Yeah, this is the energy. Cool. Hopefully, if my physics is not completely bad. Okay, so yeah, you got angular velocity, and you also got this thing. Angular velocity was this thing, and the energy is this. So omega is, and now you can just put eta as capital upon small m up here, right? So this will be 2 small m upon 2 small m plus capital M, right? That times g times t upon r, of course. G upon r p. Cool. And what else was there? Our kinetic energy system. Wait. Do you mean the energy of the wait? Is that the thing? No, the kinetic energy. Right. Then it's okay. Then you can do this thing. Go. It's like okay, gravity is an external force in that case. If you actually meant the energy, you would also take the Earth into our system, and that would just become so much tough. With whatever. Actually, no. The energy would remain constant. So you just figure out the potential energy at the first point, and there you go. Actually, that's much easier. In fact, depends on where your potential energy zero mark is, whatever. So that's awesome. And kinetic energy is a function of time. You got this thing. So once again, eta is just capital M upon small m. Put that in there. It's going to be what? Like 2 small m plus capital M, and you got small m. It's like, okay, m squared is, how does that work? No idea. So m squared, g squared, t squared. Wow. And all of that upon this guy. So 2m plus capital M. Perfect. Next question. Hey, is this dimensionally correct? First of all, so gt is velocity. This whole thing is mass. Yeah, it is actually 244. Uh, the ends of thin thread, okay, tightly wound on the axle of radius r of Maxwell's disk are attached. So no figure is given. What is a Maxwell's disk? I think this was a Maxwell's disk, right? This thing, was this the Maxwell's disk? Whatever. Are attached to a horizontal bar tightly wrapped on the axle. Axle. What? Look, first of all, I'm not sure what a Maxwell's disk is. As much as I remember, it was this thing. right? It is this thing. So, the ends of thin thread tightly wound on the axle. But where is the axle? I think this might be the axle, right? They also didn't give us any figure because, oh, that would have helped us, right? To horizontal bar, when the disc unwinds, the bar is raised to keep the disc at the same height. The mass of the disc with the axle is equal to m. Moment of inertia of the arrangement related to axis is I. Find the tension of each thread and the acceleration of the bar. Each thread, what? Uh, Attached to a horizontal. Look, I have no idea what's going on. Maybe, okay, they didn't given us a figure. How am I supposed to do this thing? Why is the bar is released? A horizontal bar. Okay, no, I'm just skipping this question. I have no idea what's going on. 245. A thin uniform rod AB of mass m and length L can rotate freely about vertical axis passing through its ends. Okay, through its end A, not ends. Okay, cool. So this end is A. It's a thin horizontal uniform rod AB. Okay, mass m, length L. Fine. What about it? Certain moment the end P starts experiencing a constant force F, which is always perpendicular to the original position of the stationary rod. Perpendicular to the original position of the stationary rod. Wait, what? Directed in a horizontal plane. Uh, this is the original position, and you want always perpendicular to that. Huh. Okay. I think I get what's going on. This is a constant force, right? And wait, okay, it starts experiencing a constant force. But that just means like, okay, this guy's velocity in a particular direction is always, sorry, acceleration in a particular direction is always constant. That's bad actually, right? So if I take this, uh, yeah, if I think out like this, so you got, right, first of all, you got a force in this direction, so it's got some acceleration in that direction, right? But then after the while, it does this thing and still has that same acceleration in this direction, right? Yeah, but wait, won't there be another acceleration? So I mean, you can only have acceleration like this and like that. So then you have to actually make components of this thing and whatever. No, but if this actually always happens to have the same acceleration, it's gonna go like this. It cannot go in a circular fashion. So what's going on? Why is this happening? Find the angular velocity of the rod as a function of its rotation angle phi countered relative to the initial position. This is weird. Once again, I don't know what's happening. And just B feels the, maybe it's like this. Okay, maybe you got something like this thing. So you got a charge at this end, and you got a constant field or something like that. So there is this force, sure, but there's also the force because of this rod itself. So it still goes in a circular orbit, circular motion, right? Is that how what's happening? I think so. Right. Then yeah, okay, find the angular velocity of the rod as a function of its rotation angle counted related to the initial position, right? Okay, it's doable, no big deal. So of course it's doable, right? It must be doable. On this complete rod, you got force in this direction of, this is weird. Uh, hey, you can actually figure out the velocity of this, speed of this thing, right? So this force, it does no work on this thing, right? There's, yeah, that's awesome. So this just this force and this is getting complicated. Are we sure there's no force in this kind of direction? Well, there can't be. It's a rod. It's right. That's a weird assumption. Why can we say that there's no force in this direction? There can be, right? What if there is? Okay, that's not the way to do it. Just use torque equations and get the thing done because you definitely don't want to be doing this thing. Right. Okay, this is getting complicated. Um, Anything else you can do? Energy conservation, most likely. Yeah, energy conservation. So think about it. The force at this point, the point of application of this force is not moving. So no power delivered by this force, right, at the hinge point. Cool. And that just means you can do energy conservation. So the work done by this accelerative force, so force F was it? Right. So it's gonna be F times this length. So you got angle phi. This length is L, so it's L sine phi. So F times L sine phi, that's the work done by this. That's just equal to half I omega square. So half plus linear motion. All right, half inertia is just ml squared upon 3, and then you got omega squared. So there you go, you got the angular velocity. What do you want exactly? Find the angular velocity as a function of phi, of course. We got it. Easy as that. Though it took a bit of understanding what's actually happening over here. They should have actually told us that, this force is external and not the net force, whatever. So ml omega square upon 6 is equal to f, so it's equal to 6f basically. There you go, you got omega is equal to square root of 6f upon ml. That's our answer. Next question. 246. 246 is in the arrangement shown in the figure 1.56, this thing. The mass of uniform solid cylinder of radius r is equal to m. What? Okay, cool. And the mass of two bodies are equal to m1, m2. The thread slipping and the friction in the axle of cylinder are supposed to be absent. Alright, so there's no slipping. Okay, cool. And the friction in the axle is 0. Find the angular acceleration of the cylinder and the ratio, okay, of the vertical sections of the thread in the process of motion. So you want angular acceleration alpha, and you also want the ratio of tensions T1 upon T2. Okay, cool. Of the vertical sections. Right. No big deal. We can do this thing. Cool. Yeah, right. So is energy conservation gonna work in this case? I don't think so. I don't think so. Yeah. You could try doing it. The tension is always in this direction, and then as this thing, so yeah, it's like alpha r, and then you integrate that thing. So amount of thread that has bent down, basically, right? That's the work done on this guy. So the amount of thread that went up, work done on this guy or something like that. Yeah, so the T dot X method, that's what I'm trying to do. But for a different system than just masses, you also got this pulley, which is a mass now. Okay, weird. Right, so this goes down and this goes up, so you got M1. Okay, suppose you do that, and then it's weird. At any given moment, um, right, the velocity of this complete thread, so the speed of this complete thread is the same everywhere, right? We could use that fact, I think, to our advantage. So suppose it goes down by x and this goes up by x. The work done by gravity on the system is just m1 minus m2 times g times x. All right, and that is equal to right. What was the thing once again? Maybe that's not the best way to do this thing. Maybe we just, yeah, maybe just doing the usual stuff is better. But who knows? It could be something better, right? For all we know. So let's try it out. So m1 minus m2 gx, that is equal to the total energy that you got in this case, right? Kind of energy, of course. It's getting complicated. Equation, whatever. And you want the tensions as a function of, right? First of all, you want alpha, right? Once you got alpha, maybe you can do this thing. Yeah, you would actually want to. Hey, so if you know what the acceleration is, then that is basically telling us that You can just figure out what this is. Oh yeah, that's actually nice. You just use the force analysis on this guy and get T1 and T2. Hey, that's actually not that bad after all. So let's do the thing. M1 minus M2 times G times X. That is equal to the energy of this whole thing. So you got M1 half M1 V squared plus half M2 V squared, and then this guy. So you got V upon R as the inertia, so as the velocity, and then you got half inertia of this thing, which is m r squared upon 2, and then you got V upon R squared, so V squared upon R squared. This is going to be mv squared upon 2, right? Yeah, it's just equal to half uh, m1 plus m2 plus m upon 2 times V squared. Cool. So then just differentiating this thing, you just get m1 minus m2 times g times v is just equal to, that goes on the, yeah, like m1 plus m2 plus m upon 2 2v dv, you get the thing. So like v, and then you got the acceleration actually, so dv upon dt, isn't that right? This cancels. Wow, awesome, isn't it? A, just figure it out without actually any analysis. Wow, that is actually a better way of doing this thing. I could always do this, right? Yeah. And moreover, it's not just limited to this kind of system. We could actually generalize it. Why I have not been using this thing, but why? Why not use this? This looks awesome, doesn't it? Exactly. This does look awesome, right? Cool. Let's do the thing now. So you got the acceleration, it's just gonna be m1 minus m2 times g upon m1 plus m2 plus m2. There we go. So any system that involves a thread, which, so a single thread, which moves at the same speed everywhere, you could use this fact, right? And just do this thing and get the thing done. Cool. Right, I'm going to use this for sure. So T dot X would not have worked because the tensions are different everywhere. So yeah, but this method, it works somehow. So like, okay, T dot X, why would it not have worked? How do you use T dot X? You worked on by the tensions is 0 or something like that. Oh yeah, the pulleys, the, yeah, like that thing. You don't take those into account, right? Mhm. In this, you have to take those into account. So right, T1 and T2 are not the same, and that's why you have to do that. Right, right. Now it's starting to make sense. Cool. So you got the acceleration. Now, what do you want? Oh, and first of all, what is T1 and T2, right? So T1 is just equal to, I should say, okay, mg minus T1 is equal to ma. So T1 is equal to mg minus ma. And T2 is equal to mg, oh, it's like m1g, right? So m2g plus m2a. Sorry. And also you want alpha. Alpha is this thing upon r. Perfect. So you got the first answer. Angular acceleration. Which is equal to this thing. So m1 minus m2 upon m1 plus m2 plus m upon 2 times g upon r. All right. Yeah, and what else? Right, T1 is this thing, T2 is that. You just want the ratio of these guys, don't you? So T1 upon T2, that's gonna be this thing upon that. So M1, yeah, okay, actually I have to maybe define some stuff first of all. Not really. So those G's will cancel. We'll just say M1 times this denominator first of all. So M1 plus M2 plus M upon 2 minus M1 times the numerator, because you know the thing, cross multiplication and everything. So M1, you got M1 minus M2, right? Upon m2 times all of this, so m plus m2 plus m upon 2 plus m2 times m1 minus m2. Now let's do the thing. So m1 squared cancels, right? You can get rid of these guys. M2 square cancels. Perfect. Okay, that doesn't cancel right now. Fine. So you got m1 m2 plus m1 m2. So you got 2 m1 m2. All right, and you got this thing. So m1 m upon 2, and then over here you got 2 m1 m2, just like that. Yeah, and you got plus m2 and m upon 2. Perfect. So 4m1 m2 plus m1, right, upon 4m1 m2 plus m2. Right, that's the thing. So T1 upon T2, you got the thing now. T1 upon T2 is just mm1 plus 4m1 m2 upon mm2 plus 4m1 m2. Right, symmetric as you would expect. Next question. 247. 247 is in the system shown in figure 1.57. Where is 1.57? I think here. Okay. The masses of the bodies are known to be m1 and m2. The coefficient of friction between the bodies, the body m1 and the horizontal plane is equal to k1, and a pulley of mass m is assumed to be, right. So masses are given. Wait, what? The coefficient of friction. Oh, okay. And the horizontal plane. Huh, interesting. Pulley of mass m is assumed to be uniform disk. Thread does not slip over the pulley. At moment t equal to 0, the body m2 starts descending. Assuming that the mass of the thread and friction in the axle of the pulley to be negligible. Find the work performed by the friction forces acting on the body m1 over the first t seconds after the beginning of the motion. Sure. So t second has been right. You just want time dependence of the displacement, and then you will have the thing, right? So if it goes down by displacement x, right, the work done by gravity is just m2gx, right, and the work done by friction is negative. It's just negative mu m1gx, right, and that just yeah, that's right, and that's just equal to the change in the kinetic energy of this whole thing. So you got m2 v for all that stuff. So you got, yeah, who am I kidding? Just do the thing, you know, just do the thing, right? You're gonna have that acceleration in any case, right? Yeah, just like the last time. So you got m1 plus m2, half m1 squared, half mv1 squared. Take the derivative of that thing, 2v acceleration, half cancels, all the same process, right? Don't have to repeat that. Just for this mass, you're gonna have half of half mv squared, so like 1/4 mv squared as the kinetic energy. So the derivative of that thing, you're gonna have the m upon 2 factor. So there we go. Right, so you got the acceleration without doing anything. Huh, isn't that awesome? So m2 minus mu m1 g upon m1 plus m2 plus m.2. Perfect. So now that we got the acceleration, just, yeah, just half 80 squared. So m2 minus mu m1 upon 2m1 plus m2 plus m g times t squared. That is the displacement. So this times the force of friction, and you'll be done basically. So the work done is just mu mg, mu m1g, I think, right? Yeah. There you go. That's the work done by friction. Actually, it's negative of that, right? Right. So that should be the thing. So our answer is negative. Okay, just work out. Mu m1. You got m2 minus mu m1. Assuming it actually does go down. And if it doesn't go down, it won't go down ever. So yeah. Upon this, so 2. Hey, isn't it supposed to be 2m2 as well? Yeah. 2m1 plus 2m2 plus m, like that. And then you got what? G squared, t squared? Right, that's the thing. Next question. 248. The uniform cylinder of radius r is spin about its axis to the angular velocity omega naught. So figure 1.58. Okay, it's spin about its axis to angular velocity omega sub 0, and then placed into a corner. The coefficient of friction between the corner walls and the cylinder is equal to k. So you just placed. I mean, it doesn't have any velocity right now, does it? Okay. How many turns will the cylinder accomplish before it stops? What? So there's friction in this direction or whatever. There's also friction in this direction as it's moving. Wait, what? Okay, friction in that direction, huh? Interesting. But that would just mean like, okay, the normal force in this that, hey, that's weird. Okay, the normal force will not actually try to push it away. It will just, okay, this will not push it away. It will just not let it go to the left anymore, right? That's all you have to do. So friction and normal, well, they cancel each other in any case. Just do the torque equation for center of mass, right? I hope so. Okay. How many turns before it stops? Hmm. You know what? I'm starting to think of something that's not right, not what I would usually do. Since I've been doing these using energy conservation, sorry, the work energy theorem. Why not do this one as well? So first, just a bit of forces so that we can get that relation between frictions and whatever. So you got a normal force in this direction. You got an upward friction force, right? We call it F2. You got a friction force in this direction, F1. Normal force will actually be equal to this upward, so will be equal to this F1, right? Yeah. And since it's moving and everything, it's actually going to be equal to mu F1. And for now, let's call this thing as F because, yeah, cool. And then you also got this normal force, so we could actually say this is actually mu times n, right? Mu times n. It's mu times n over here, and you got mu squared times n, right? Okay, and now let's do the vertical force balance. So you got mu square n plus n is equal to mg. So you got normal force actually. It's just mg upon mu squared plus 1, right? So this friction, you got the thing, it's just mu times n, and this is like mu squared n. The Right. So suppose it like shifts by r d theta. So this point shifts by r d theta. This is by r d theta. The work done by friction or the negative work done is just equal to r d theta times this. So this friction force and this friction force, sum of that, right? So r d theta times this friction force plus r d theta and this friction force. Make sense? Cool. So that's just going to be what? Mu n times mu plus 1. And what is mu n? So n is just this thing. Just put that in there. So r d theta. Um, and you know what? Actually, no. Let's not use d theta. Just use theta by itself. Because yeah, I mean, after integration, you're gonna get that thing in any case. So just use it directly. So you got mu mg upon mu squared plus 1, and then you got mu plus 1. Perfect. This is the work done by friction, right? And this is just equal to the change in the kinetic energy, or it's the negative of that actually. Perfect. So yeah, this is going to be the loss in kinetic energy actually. This left hand side. So initially, okay, just do the thing actually. Half inertia is just mr squared upon 2. And then you got omega initial squared minus omega squared, right? Yeah. And look at that, would you? It's a differential equation basically. Isn't that right? Exactly. Yeah, it's a differential equation. So using this, you can just, figure out when is this going. Actually, you know what? No, just put omega equal to 0. You don't need to solve to get the theta value. Just put omega equal to 0, you get theta value by itself. And once you know what the theta value is, just divide by 2 pi, you get the number of terms. Perfect. Yeah, that's the most perfect method to solve this thing. And why did I never use this? I should from now on, of course. So you got mu times mu plus 1 upon mu squared plus. Why did they not give us some value for mu squared plus, so for mu? That would have helped us. Okay, that's theta and everything. And you got what else? Mg stuff. Okay, that's just equal to hey, so the mass is actually the same, right? Cancel that out, right? Even though that's capital M, it's the same thing. So r squared upon 4, and then you got this g, so 4g. And then it's going to be 0 at that moment where you want the theta. There we go. Yeah, so theta upon 2 pi, that's going to be equal to mu square plus 1 upon mu square plus mu. Let's call it like that, So mu square plus u is better, I think. Okay, all of that times this. So omega naught squared r squared upon 8 pi g. Yeah, that's right. That's right. This is the number of turns that it will take. So n. Cool. Next question. 249. A uniform disk of radius r is spin to the angular velocity omega and then carefully placed on a horizontal surface. How long will the disk be rotating on? So it's time basically. Okay, fine. Be rotating on the surface if the friction coefficient is equal to k. The pressure exerted by the disk on the surface can be regarded as uniform. Why do you give us that? Huh, whatever. How long will the disk be rotating on the surface if the friction coefficient is equal to k? Okay, this is... Wait, no diagram, huh? um, there are two things that I could be doing. So the first one is like maybe you just place the disk like this. So that's what I'm thinking right now, that's what they did. But in that case, asking how long will it be rotating? I mean, it's gonna rotate forever because right, first you got some friction to actually give it velocity and whatever and make v equal to omega r in the end. And once that happens, it just keeps on going forever. So, then that means this is not the thing that's happening. So this is the ground, this is the disk. You get the thing, right? The other thing is, what if, the disk is horizontally placed? This is the ground actually. This is the ground. The disk is placed like that. It's rotating like this thing, omega naught. Huh, that's weird. That's omega, right? Yeah. And the pressure is uniform and whatever. Okay, so that's why they gave us the pressure to be, right? Because there is an actual area in this case that there it was not. In right, but now here is an area, so you have to do the thing. Okay, so the pressure is uniform. Wow. If the pressure is uniform, what is the pressure, by the way? It's just equal to mg upon, this is getting complicated, but you have to do it. So it's mg upon the area, which is pi r squared, right? Okay, you got the pressure. Now for a small element dA, what is the torque produced by that, the friction at that point, about the center of mass? That's weird. So we just want the angular acceleration because of friction at any given moment. Once you figure that out, it's just divide by angular value, right? Okay, you have to actually figure that out first of all. And this thing that the pressure is actually uniform, I am still doubtful about this. How can you say that? I don't know. Might be true, might not be. Whatever. Let's do the thing. So because of a small area, dA, the mass of that area is of course just what am I doing? Okay, the surface density. So the surface density is just m upon pi r squared. Okay, yeah, let's not use that thing. Not doing that. Instead, we'll just go with this thing. The area times the pressure. So PdA, that's the normal force at that point, right? The question of friction, which they are, I think, calling to be K, right? Okay, so K. Yeah. Oh, over here it was K as well, and so I should have written K. But whatever, whatever. You know what? No, let's not use K. Let's use mu because that's what I'm using all the time. So mu PdA, that's the friction, and it's at distance r. So r times of that, and yeah, it's actually going in that direction. So it's going in that direction. Whatever. So it is going to be r actually. There we go. You got the d tau. So right, d tau is just this thing. Is that right? I think so. And then what is dA really? dA is r d theta and then dr, because sure, that's this thing, that's r d theta, and then you got this, that's the word dr, and yeah, this kind of square area is this thing. Okay, awesome. And now we can figure out what the torque actually will be, and it's not a vector anymore. Just think what's square, scalar. So integration of this guy. Um, yeah, well, r is actually a variable, right? So you got what is this thing? Integration. The mu is out, p is out because those are constants. You got r squared, dr, and then d theta. So it's the integration from, well, through the whole area, of course. So we'll just break it as two integrals, one for theta, one for r, because they're independent anyway, right? The theta integral will just make this equal to 2 pi. So that's awesome, I guess. And this integral is going to be r cube upon 3, capital R cube, of course. There we go. You got the torque. Uh, I hope it's correct. So you got 2 pi mu and then r cube upon 3. And now we'll just put what pressure is there. So it's mg upon pi r squared. Oh, r should be capital. So yeah, this cancels r squared. So one of them cancels. So the torque is just this thing. Torque is, yeah, 2 mu upon 3 mgr. This is dimensionally correct, of course, because force times radius. Okay, so then we talk upon inertia. Inertia is what? It is mr squared upon 2 because it's disk, right? So mr squared upon 2. And then divide, so you get angular acceleration or deceleration or whatever you want to call it. This cancels, okay, that's r, right? It's going to go up 4 mu upon 3 g upon r. Finally, you got the thing. So the time required is just omega upon this. So you got 3 omega r upon 4 mu g. You got the thing. Next question. That's awesome. Actually, you know what? No, I'm gonna keep some results from this thing. So the torque, right? You can keep that. Um, yeah. So in terms of pressure, that's actually the one I want to keep. Actually, no. You know what? I can derive it at the go. I don't have to keep it in the end. So whatever. Just delete everything. So you got the time required. Okay. What? 250. A flywheel with initial angular velocity omega naught decreases due to the forces whose moment relative to the axis is proportional to the square root of its angular velocity. What? Sorry. Um, Initial angular velocity omega naught. Okay, it decelerates due to the forces whose moment relative to the axis is proportional to the square root of its angle. So, okay, cool. Our angular acceleration is proportional to, okay, alpha. Wow, not good. It's proportional to or deceleration. So yeah, okay, negative square root of omega naught, right? Okay, sorry, square root of omega, not omega naught. What was the thing? Once again, yeah, this is right. So initially it was just omega naught, and now it's this thing. Find the mean angular velocity of the flywheel average over the total deceleration time. All right, okay. The mean angular velocity. Wait. Oh, you just want the theta basically, right? Okay. I understand this fine. And you also want a time of when it actually stops. Oh god. Is there some easy way to get this without actually going through all of this? Without, why am I so screwed up? It means just a simple calculation, right? So just, yeah, okay, d omega upon dt is just equal to negative k square root of omega. Just use the thing and then negative d omega, whatever. Omega upon negative 1 upon 2. Increase 1 upon 2, you got 2 square root of, yeah, this should work. Just equal to k times t. All right. Okay, it's actually going from something to something. So we should say it's square root of omega naught minus this. Okay, I need even more space for this thing. Square root of omega naught minus this thing. All right, cool. And also you would like to have theta. Oh, you don't want to get this. Ooh, not good. Because getting theta is a painful thing. Isn't that right? Um, yeah. So you want to get theta, it's like integration of d theta, which is integration of omega times dt, of course. And then divide this by the time required, which is integration of dt. What is dt, by the way? It's like d omega upon alpha, you could say so, right? Yeah, or negative alpha, whatever. So d omega upon alpha. This is like just d omega. Hey, that's better, isn't it? But yeah. Um, No, okay, that was dt, sorry. So you got d omega upon alpha over here as well. Hey, that's actually much better because you want to integrate over omega in that case, right? Yeah, that is actually much better. So omega, this is like d omega square upon alpha. Ah. Oh, it's like almost like that thing about, okay, whatever, just not doing this. Fine, that's what matters. That you got theta, you also got time. Just divide these things, of course. And now just don't do all of this, right? That k will cancel whatever. You don't need to do all of this. It's gonna be integration omega d omega upon just put square root of omega. That negative and all that stuff, no need for that. It's gonna cancel out anyway. And then this is just this um, upon the integration of d omega upon square root of omega, and then you could use those negatives to switch the integration limits. So you could go from 0 to omega naught if you really want that negative over there. Okay, just want to do this integral and then you are done. Hey, that's much better than that, right? Of course. So it's like omega power 1 upon 2. So integrate that. It's going to be 2/3 omega power 3 upon 2. So you got omega naught power 3 upon 2 basically. Upon power negative 1 upon 2. Let's get 2 omega power. Is that right? Of course it's right. Of course. What could go wrong? So 2 omega power 1 upon 2. Right? So it's like 1/3 omega power 1. So okay, omega naught. There we go. That's the thing. So 250 is just 1/3 omega. I could use this thing instead of actually figuring out theta and everything. Yeah, that's much better. There we go, 1/3 omega naught. That's the average. All right, next. 251. Wait, you know what? No, let's stop over here because 250 is a nice number. So that's it. I'll see you in the next video.